So now that we've looked at the basics of propositional logic and a few different examples and applications of them, what we want to do now is start to abstract things a little bit. And with that abstraction is going to come more power. So similar to how, like in mathematics, you move from arithmetic to algebra to calculus, you start to get higher levels of abstraction, but you also get higher levels of power. Similarly here, we are going to abstract things even further, which will then allow us to have more tools in our toolbox, more advanced tools to be able to more deeply analyze different algorithms. And so the first thing that we're going to start out with is, you might have noticed that everything that we've been looking at has usually relied on truth tables. And truth tables can get pretty tedious to have to write down. So if you've written out a very long proposition, compound proposition, has a whole bunch of different variables inside it, it can get tedious to write out those different truth tables. So the first thing that we're going to look at is how to manipulate compound expressions. This is really the motivation behind this, is quality of life. You don't want to have to keep writing down truth tables whenever you come across a logical statement. You want to be able to quickly be able to relate them to other logical statements. So that's really the motivation behind this section right here. And it's going to involve three main parts. And so the first part is identities. We're going to derive a few different identities. And these identities are going to give logical equivalence between different compound expressions, and that's going to make our life a lot easier so we don't have to keep checking truth tables. Secondly, what we're going to look at is revisiting implication and by implication. So implication and by implication are extremely foundational, especially in the analysis of algorithms. And so it's going to be pretty crucial to relate these couple of quantities back to the identities that we are going to derive. Lastly, the thing that we're going to look at is being able to prove logical equivalence without truth tables. So as a motivation here, if you want to be able to show that one particular algorithm is in another complexity class as another algorithm, you might have to be proving some sort of by implication statement here. Or you might have to show that a couple of different compound expressions are logically equivalent, and you really don't want to have to be writing down truth tables. And so what we're going to do is combine up these couple of things to be able to prove logical equivalence without actually having to use truth tables. The next thing that we're going to look at is we're going to revisit propositions. So you might have noticed that so far, most of the propositions that we've been looking at have been pretty simple. So for example, we've been looking at things like you get 100% on the final exam. So if we wanted to replace this little 100 right here with something else, like say 99, right now with the tools that we have, what we'd have to do is we'd have to define a whole new proposition that would look like the following. You get 99% on the final exam. And you can immediately see how tedious this would be if all we want to change in these couple of propositions right here is this little number right here. We'd have to define a bunch of different variables for all those guys. So what we want to do is be able to introduce a concept of parameterization, or said another way, introduce variables into our propositions right here. So basically what we want to do is to be able to take a proposition right here and replace it with something like an x right here. And when we have an x, then we will be able to change that value of x to be able to get a whole different range and a whole different class of propositions. So the second part of this unit 2 right here is going to be predicates and quantifiers. So this is not an official definition right here. It's just a way to think about it, that a predicate is a way to introduce a variable into a proposition. So replacing this 100% like with an X or something like that. And the motivation why we'd want to look at predicates is that you would want to prove some statement about your algorithm for, let's say, every single one of its inputs that is acceptable. And so you don't want to have to write down a different proposition for every single possible input to your particular algorithm. And so what we're going to be able to do with predicates is introduce basically a statement that stands for every possible input to your particular algorithm. Second part is quantifiers. So for example, with your algorithm, you might want to have a proof of correctness, and so that you want to say that this algorithm here is going to work on every possible input. And so you want to quantify what different values of those variables right there your algorithm is going to return a correct answer. Or maybe your algorithm is spitting something out. And so let's say that your algorithm, produces a graph with a certain property. So you might want a quantifier that says something like, well, given some special kind of input, some special kind of variable right here, it's guaranteed that my algorithm is going to output some graph with this property, etc. So quantifiers are going to tell us how the variables here interact with the predicates that they're related to. And then next, what we need to do is relate predicates and quantifiers back up to all these identities and the different logical operators that we've looked at. And that's going to be the third one. And so with these more powerful abstract ideas, these identities, ability to manipulate compound expressions and be able to express things in a more verbose and more powerful language right here is going to give us more tools in our toolbox when we need to go and analyze our algorithms right here. So we're basically building up the theory to be able to get to the actual analysis of algorithms.